Leetcode 133, clone graph. Given a reference of a node in a connected undirected graph. So first sentence, and we already have a lot of informations. First of all, we have nodes. So the structure on which we operate is called graph, and individual elements are called nodes, and those nodes can be connected through edges. And the thing that is worth noticing here is that at no point in the code, we will deal with one object or one structure called graph. We only operate on the individual elements, which might be a little bit confusing if you are new to those kinds of problems, but this is kind of standard. So usually we just have those individual parts, but not the whole structure itself under like one name or one object. And the graph has certain characteristics. So for example, here it's already said that it's connected and undirected. And both of those things, both of those characteristics simplify our problem a little bit. So connected means that from each point in the graph, I can reach every other point. So we don't have, for example, individual islands of nodes inside the graph, which are kind of disconnected, as everything is connected together. And undirected means that if I can go from point A to B, I can also go back from B to A. So there is no directions on the edges. It's undirected. And here is our task. So the second thing is return a deep copy, a clone of the graph. And next they describe what do they exactly mean by a node. Each node in the graph contains a value, an integer, and a list of nodes, so a list of objects which it's referencing, its neighbors. And here is a code example, class node, public int val, and public list of nodes neighbors. Yes. So every time when we have nodes, we will have some data that it stores, and then the references to the neighbors to which it's connected. And so there are various ways in which we can do, but this is kind of standard. And one thing that's worth noticing is that the data that it stores is a number. And a lot of times it's a bit confusing, at least for me, because the input will also be given usually as an array of numbers, and array itself has indices, and sometimes those indices, which are also integers, mean something and so on. So you will have a lot of numbers and you kind of have to wrap your head around that. So I prefer when we have, for example, nodes in a graph or in a tree that they store letters. Yeah? Because in that case, it's kind of easier to differentiate between index in an array and actual data that you store and so on. So that's just a minor note. And let's proceed. So for simplicity, each node's value is the same as the node's index. And they start with 1. So 1 index, for example, the first node, and the value is equal to 1. The second has the value or the data that it stores equal to 2, and so on. The graph is represented in the test case using an adjacency list. And here is a confusing part. We will see it in a second. So here they introduce adjacency lists, but in the code itself, they don't exist. So if anyone has a theory why it happens, so then please explain. The only thing that I can kind of guess is that maybe this problem is a bit like the description itself is a bit older, and at some point they change the code, but who knows what happens. But nonetheless, let's refresh adjacency list. It's also important to know when you study those kind of problems, and that you have multiple ways of sort of representing a graph inside the code. So there's like adjacency lists. You can also use dictionaries, and there are some other ways. And dictionaries are usually the easiest, but let's see what they say about adjacency lists. So this is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in a graph. Yeah, so in that case, you have like one big list, and inside each element is also a list. So you have like a 2D list or a matrix, and the index in this bigger one would be corresponding to some node or some value in a node, and then this inner lists would be the neighbors themselves. And the given node will always be first node with value equal to 1. You must return the copy of a given node as a reference to clone graph. Okay, so here is some graphical example. We have 4 nodes. This is the input, the original graph, and each one has 2 connections. So one is connected to 4 and 2, 2 is connected to 1 and 3, and so on. And we cannot just return the same graph itself. And point to make, we are not operating on a whole graph, which is also kind of confusing when you read this diagram. We are just returning a single node, the first node in the graph. Yeah, so that's the thing that we have to return, and we cannot just return the original one, the one that they are giving us. So this makes a little bit more sense. How could they verify that? And because if they would give us just adjacency list, which is not doesn't have node objects, just integers themselves, then it would be hard for them to verify if we did that thing or not. So maybe it's something strange with the description, but however, let's assume that the version that's in the code itself that we will be sending, it's the one that we should care about. Yeah, so there will be no adjacency list, just mentioned here. And if we return like the original one, that's not allowed. We have to copy it, so we have to create as many objects of this node class or of this node struct, and that was given in the input. And we have to, for each object, we have to fill those 2 fields, so in the same way. Yeah, so those have to be copies, but have to be filled in the same way. So we have to put this value, so the data that it stores, the same as in the original, and also neighbors, which would be referring to the neighbors with the same values as in the original, but also from the cloned version that we will be creating as we go. So that's the good option, and here is the wrong option. The nodes were cloned, but the graph is messed up, doesn't have the same connections. Yes, so we have to go care about the connections. So what happened here, for example, they swapped 3 and 2, yeah, and that's not good. So in the original, there was no connection between 1 and 3, and here there's connection between 1 and 3, and that's not allowed. Yeah, so we have to keep track of all the values and all the references and just recreate that graph from this single node that is given as input, and we have to return a cloned version as an output. And here, of course, inputs and outputs are referring to this adjacency list stuff, which has nothing to do with the actual solution. So let's maybe draw a graph and think about a couple ways in which we can tackle this problem. So we can have following graph. Let's use letters for the values or for the data that is stored in our nodes, and let's make it like this. C, here B, the bottom D, and one more to make it a little bit more interesting. We will start here, our starting point, and the graph itself is undirected, so we can connect A with B and D, B with A and C with B and D, and D with E, sorry, and but also with A and C. So D has the most connections. Let's maybe also write it down. So A has the following neighbors, B and C. That's our example graph on which we will try to come up with an algorithm how to clone any graph which meets the constraints of being connected and undirected. So the next one would be B. B is as the following neighbors A and C. The next one would be C, which has B and D. C has the same neighbors as A, and D has neighbors A, C, and E. Yeah, so that's some made-up example on the story. I think this one. No, not this one. Selection. This is that I want to move it a bit to the side so we have some space here to come up with the algorithm itself. So we have to the task is to clone the graph of keep the values and connections in the unchained. Let's more. Let's put it in some rectangle. So it stays with us. That's the task. Move it here to the left. And now we can have a couple of approaches. So generally we want to go through each element. To clone everything, we have to somehow go through everything first. So that's called traverse. Graph traversal is the thing that we have to do. And there is always two basic algorithms or which we can choose from, DFS and BFS. And just I will not go deep into the differences between them, but just to kind of short reminder of what even we mean by that is that DFS goes as deep as possible. So you start with one element and we will choose DFS for that. And I will explain in a second why. And then you go to one of its neighbor, and then from that neighbor to one of its neighbor, and so on until you reach an end, or either you traverse the whole graph that way, or you will reach some point in which you have no neighbors left, and then you have to go back, kind of backtrack one level up and check if you traversed any neighbors of this one element above, and so on. So this one is more of it's the depth first search. So you go as deep as possible first, and then you backtrack, and its competitor or the other option that we have is a BFS, which goes kind of floor by floor. Yeah, so first you choose one element, then go to all of its neighbors, not to the single one, but to all of them, and then you go to the neighbors of the first neighbor, and so on. Yeah, and you always visit all of the neighbors that are available, or in case of DFS, you just go to a single one, and then as you backtrack, you visit them. You visit those that you haven't visited yet, and so on until you visit everything. Or in case of disconnected graph, you will not visit everything. But here everything is connected, so we can choose either that or that. But for BFS, usually both of them have couple ways in which you can implement it. But for BFS, usually you need an additional structure, queue, in which you are queuing the neighbors that you want to visit. And DFS a lot of times is simpler in a sense that it's easier to write. Yeah? So in the case of that problem, we could choose both, but I'm choosing DFS simply because I think it's a little bit simpler to implement. But the difference is not that big in that case. So how will we traverse it using BFS? So we already said that we start in A. So let's maybe mark it down first that we have chosen DFS, and now we will be traversing it first, like on this diagram, and then we will implement the traversal in the code itself, and as we will be traversing, we will be cloning. So for the clone, we can already create an additional structure. Cloned. So the first thing that we decided on is that we have to traverse. Then when we decided on traversing, we need to decide how. We said that we will do it using DFS. And as we will be traversing, we will be using an additional data structure that I just decided it will be called cloned. And we will be adding new elements to it, which will be analogous to the elements in the original graph. Yeah? So we will keep track of both the data that they store and also all the neighbors. And we start with a single node. Yeah, that's what they provided us here with, and that's our input in the code. So we can even mark it down here as well. Let's start. We start here. We could start wherever, but we have to pick up one node. And from that point, we will go through the whole graph using DFS, and we will be modifying our cloned data structure. So let's write down what will happen. So the first thing is we visit A, and in that visit we clone A and pick first neighbor, and the first neighbor is B. Oh, that's the first thing that we would do. Oh, that's the first iteration now. So we picked B. Goes here, and cloned A goes here. Make it like that. So the first node has been cloned, and then we do the same for B. We visit B, and we clone B and pick first neighbor, which hasn't been used yet. For example, B has the following neighbors A and C, but A is used already, so we cannot use it. So we pick C. And that's the second step in our algorithm. And the third step would be visit C. We clone C and pick the first neighbor, which hasn't been yet visited. And B has been visited. We are not picking it, but we can pick D. Kind of like this. Yeah, that's then is the course. Yeah. As we go, so in the second step, we should also update our cloned part. So we add here B and C, and that's the cloning part. And the fourth step will be visit D, clone D, and pick the first neighbor that hasn't been used, and that's E. Now, so in that case, we already used this, and the only one left is E. And in that case, E doesn't have any more neighbors that haven't been used. So we kind of used everything at that point. So we stop. Also, we would add D, and yeah, the fifth step would be visit E, clone E, and pick the first neighbor, which doesn't exist, so we don't have any more neighbors. That's it. Quite simple, I guess. Let's try to implement it inside here. And we will have EFS, which we return here, and we need to have our structure of cloned, and that's more or less it. Rest guess is implementation detail. So because they already used the name node here, we can use underscore node in our DFS, and because DFS is recursive, well, there is also a non-recursive version, but in our case it will be recursive. We will have base case and recursive for the normal case, and the base case is simply checking if we already cloned it. So if node, we can just what was that structure of that node? We can just save the values, I guess, because they should be unique. I think that was one of the constraints. Somewhere here at the bottom, yes. So node value is unique for each node. So we haven't read the constraints because usually it's just restated what was already mentioned. But in that case, it's good to know that the values are unique. So if node value is already in cloned, then we can return cloned node value, and in the case it's not, that's already the whole base case. Normal case would be to create a new node, node using the previous node value. So the new node will be like this. Yes, I think that's how I know how it was done. So they accept in the constructor. We can already provide neighbors, or we can update them later, and the default value is 0, but we can provide it here as well. So that's how we will create a new one. We'll create a copy. And what else? We should also go to each neighbor. So for in new node, sorry, the original node neighbors, that's how it's called. We have to add them one by one to the list of neighbors, but we don't add them from the original one, we add them from our DFS. Yes, DFS of neighbor, and here return new node. And also we have to update the cloned structures, a new node new equals up, and in that case we will just go through them one by one, and for each one of the neighbors we'll call DFS. So first DFS will execute for that neighbor, we'll go through the same route, and so on and so forth until it reaches the base case, and then we'll kind of backtrack, and in that way we will traverse the whole graph, and we have to return DFS for the node that for the starting node, yes, that they are providing us with, and that's more or less it. The only thing that we can add is also to cover that optional case, so node can be none. In this case, we simply return none. Yeah, so let's say, because both ways. Let's see. Have runtime error. Not is in JavaScript. Sorry about that. Well, we passed the 3 basic cases, and now let's test on everything and see how we do. And the runtime is not that good. Let's check again. It's even worse. So let's run again then. I guess it varies a lot because there are not that many test cases, yes. Yeah, so probably we could... Yeah, that's strange, really. Usually it's not the case because there's like 200 test cases or more, and it kind of gets more stable. So if you have a good approach, you will usually be on the left side, yeah, so you will be better than 50% of the people, but in that case, it's really unstable, so I haven't noticed it before. But that's more or less how you can solve it using DFS. And if you have a better solution, you can share them with us.